All right, good morning, guys. Today we're going to be covering 8.5 secants and tangents. So let's go ahead and get started. We're going to go ahead and get started with some definitions of stuff that we should already know. The first one is the definition of a secant. A secant is a line that intersects a circle in two unique points. So we have 2 points, A and B here. And as we can see, the secant is a line that goes through the circle and it connects those 2 points together. Now, very important with a secant, it is a line, so it's not a segment here. It's just going to be a straight line. And of course, it creates a chord within the circle. So we have chord AB that is formed from secant line AB. So secants will always form chords within our circle. Now, a secant must be a line. It cannot be a segment within the circle. It can be a segment outside the circle that connects to the circle itself, which we'll learn about later today when we talk about secant tangents. But again, a secant line is just a line that goes through the circle, intersecting it at 2 unique points. The other definition that we have is tangent. Tangent is a line that intersects the circle at 1 point. So we have point D here. We see that it just touches the circle and then continues on. Now, if I have 2 points very close together, it's still intersecting the circle twice. So that would make it a secant. But for it to intersect only at 1 unique point, that makes it tangent. Tangent lines are going to be used very often. And of course, the last piece here, point D. The point where the tangent line touches the circle, that is called a point of contact or a point of tangency. So again, point D is a point of contact, otherwise known as a point of tangency. You'll see it written as both throughout these questions that you guys will be seeing. Again, line AB is our secant, and line CD is a tangent line. All right, next up, we're going to go ahead and talk about our first postulate of tangents. The postulate is a tangent line is perpendicular to the radius at the point of contact. The converse of this postulate is also true. But if I have a tangent line, meaning a line that touches our circle at 1 point, and again, the tangent line is always outside the circle. If I have a tangent line, it will always be perpendicular to the radius of the circle. And the point at which it is perpendicular is the point of intersection, where the tangent line and the radius intersect, also known as the point of contact or the point of tangency. Now again, these right angles that are created from the radius and the tangent line are extremely useful as we go through these problems. So this postulate will be used constantly within circles. So make sure that you guys do try these out. And again, this postulate, very important to remember. All right, next up. Next, we're going to go ahead and talk about tangent segments and secant segments. A tangent segment is part of the tangent line. Now, very important for tangent segments, the tangent segments will always have one of the points on the circle. Again, without a point that touches the circle, it's not tangent. So again, tangent segments will always touch the circle. One of the endpoints will always be on the circle at 1 point. Typically with tangent segments, the other point is not within the circle, but it's oftentimes shared with another tangent line. Not always, but often enough. That's typically where you see tangent lines, is when you have 2 tangent segments occurring. So that's typically when you see this occurring here. The other segment that we have is a secant segment. So we have a secant segment here. It's part of the secant line. And again, it must include the 2 intersections of the circle. So again, it must have these 2 intersections on the circle itself. Now for the secant segment, it must start on the outside of our circle. If it started on the circle itself, that'd just be a chord. But it must start on the outside of the circle, and then it must intersect our circle at 2 unique points. Now, there's 2 parts of the secant segment. There's the internal part, that's inside the circle. That's why it's called internal. And then we have the external part, the part that is outside of the circle. So that's how you're able to distinguish the parts of a secant segment. And again, it always starts on the outside of our circle and then crosses through at 2 unique points. And that is our secant segment. Our next theorem that we're going to talk about deals with tangent lines once again. Actually, it'll be dealing with tangent segments. Let me rephrase that. The next theorem will deal with tangent segments. That theorem states, tangent segments that share the same endpoint on the same circle are congruent. This can be proven using HL. Again, HL being hypotenuse leg. So if you remember way back when we were doing triangle congruency, HL is hypotenuse leg. We must have a right angle, and then we need the hypotenuse in both triangles and one of the legs in both triangles to be congruent. So the way that this theorem would look is here's how it typically would look within a problem. So we have tangent segments TO and PO. We're saying that these two will be congruent based upon this theorem, and we're going to prove it in just a second. Now we also have radii ST and radii SP. So in order to prove this, well, we know that these two angles, angle STO and angle SPO, are right angles. Because again, these are tangent lines, and the tangent line is perpendicular to the radius at the point of tangency, so at point P. So both of these angles would be 90 degrees as a result. And since they're both 90-degree angles, they're both congruent, because all right angles are congruent. From there, I can say that ST is congruent to SP, because all radii within the same circle will be congruent to each other. And that's the leg portion of HL. You already have the right angles for HL. Now we just need the hypotenuse. For the hypotenuse, I drew in segment SO. This is just an auxiliary line used to help me prove this theorem. So I drew in this segment here, SO. I said that SO is congruent to itself. It's shared by both triangles. The reason that SO is congruent to itself is by the reflexive property. From here, I can say that triangle STO is congruent to triangle SPO by HL. I have the hypotenuse, SO. I have the legs, SP and ST. Lastly, I have the right angles, which allow HL to be used. If these two triangles are congruent by HL, then lastly I can say that TO is congruent to PO by CPCTC. Corresponding parts of congruent triangles are congruent, which proves this theorem to be true. So anytime that you have two tangent segments and you have the radii for them, and those tangent segments share the same endpoint, they will always be congruent to each other, always. All right, the next definition that we have is new for us. That definition is tangent circles. Tangent circles are circles that intersect at a single point. Now right here we have external tangent circles because both circles are outside of each other. They each have their own circles, and they just touch at a single point. Then we also have internally, so two tangent circles that are internally touching each other. I can see this occurring because I have a small circle within a large circle. And as we can see, they only touch at one point, making them tangent to each other once again. Our final definitions that we're going to be talking about before we get into some examples are some that we've seen before, and those deal with common tangents. So a common tangent is a line tangent to two circles. So I already have one example on here. This is our external common tangent. It's external because it is outside the edge, it's the outside edge of the circles. It's not going in between the circles, it's on the outside edge. Now, some definitions with these. Common, whenever you see common tangents, common just means that the tangent line is shared. It's shared by both circles. Internal means that it's the tangent line that is between the circles. It's right in between the middle. And then external means it's on the outside edge of the circles. So let's go ahead and start with our common internal tangent. Again, that goes in between the two circles. And as we can see, it's tangent to both of them, touches them at one single point. And further, it goes in between the two. The next one that we have is the line of centers. The line of centers is a line segment that connects the two centers of the circle. So if I have two centers here, The line of centers connects the two of them. And lastly, we have the external common tangent, or the common external tangent. Again, that touches the outside edges. As we can see, this tangent line does not go in between the two circles. It's on the outside edge of the two circles. All right. With those definitions and everything that we've learned today in terms of definitions and properties and theorems, let's go ahead and jump into some problems. Our first problem is a common tangent problem. It says a circle with radius 8 centimeters, that'd be circle P. You see that we have a radius of 8 centimeters here for segment PB, is externally tangent to a circle with radius 18 centimeters. So I also have circle Q, which has a radius of 18. We can see that with segment QA. Lastly, we see that they have a common external tangent, segment AB. We want to find the length of this common external tangent. Further, both of these circles are externally tangent to each other, meaning they touch each other at a single point. So the first thing that we'll do here is we're going to draw a line of centers between the two circles. Now again, a line of centers just connects the two centers of the circles. And since these circles are externally tangent, it means that we can combine these two. I'm going to combine the two radii. So I have a radius of 18 for circle Q and a radius of 8 for circle P. If I add those two radii, I would get a segment length of 26 for our line of centers. Once I create my line of centers, the next thing I'm going to do is, starting from my smaller circle, I'm going to draw an auxiliary line, a line that I create that is parallel to segment AB. Now I'm going to draw that segment such that it's parallel to AB and it will intersect segment AQ. So here we go. There's my auxiliary line. And what happened when I drew this auxiliary line is it created two specific shapes. It created a rectangle above and a right triangle below. Now, before I continue, I just want to point out a few things. First off, these two angles are both right angles. Well, these three angles are right angles. Starting off with these two angles here, these are both right angles because that is where the radius intersects the tangent line. Now notice that it's not perfectly drawn because I drew this by hand. So it's off just a little bit with how the lines look. They kind of look a little bit slanted, not perfectly right angles, but just know that these are right angles. So those are both right angles because they are the points of tangency. It's where where the tangent line intersects the radius. Further, these two angles are right angles because if I drew this as a parallel line segment, well then these two angles would be corresponding angles. And we know that if we have parallel lines, then corresponding angles are congruent. So that's why they're both 90 degrees. Now, when we drew this, as we said, it created a rectangle. So some information on this rectangle, we know that opposite sides of a rectangle are congruent. So if I have a radius of 8 for PB, that means the other side needs to be 8 as well. Well, if I have the other side as 8 and the full radius is 18, then this part of the right triangle must be 10, because 10 plus 8 equals the full radius of 18. And further, I know that this has to be 8 because opposite sides of a rectangle are congruent. Further, since AB, our external tangent, is x, this auxiliary line must also be x because opposite sides of a rectangle are congruent. So if I can find this auxiliary line, then I've solved for the common external tangent. Well, since this is a right triangle, let's go ahead and use Pythagorean's theorem to solve for x. I have a leg of 10, I have a hypotenuse of 26, and I have another leg of x. So that would give us 10 squared plus x squared equals 26 squared. 10 squared is 100, 26 squared is 676. Subtracting 100 from both sides will give me x squared equals 576. From here, I'll take the square root of both sides of my equation to solve for x, give me x equals 24. Well, if x is 24, that means that our external tangent is 24. Therefore, we've actually found the length of the common external tangent as a result. All right, let's go ahead and try out some walk-around problems. So here's our first walk-around problem. We're given ABCD is tangent to the circle. So I have our circle here. I have ABCD, this quadrilateral going around it. I see that we have points of tangency as points E, H, G, and F. Those are where we have our points of tangency. Now, as a result of this, because these are points of tangency and these are tangent lines, they therefore share a common endpoint. And since these tangent lines share a common endpoint, that makes these pieces congruent to each other. So BE is congruent to BH, AE is congruent to AF, DF is congruent to DG, and CG is congruent to HC. So we have all this congruency going around because these are tangent lines and they share common endpoints, A, B, C, and D. Now, next up, I'm going to go ahead and mark up each part of my triangle as 10, 15, and 18. And that's just from our given information. We would like to find out CD. That's the only missing side that we do not have. So the first thing I'm going to do is I'm going to call BH and BE both X, an unknown variable. And you can start anywhere on this with that variable, but from there you'll need to walk around your circle. So since BE is X, that means that BH is also X, because again, they share a common endpoint. They're both tangent lines. That makes them congruent to each other. Well, if BE is X and AB is 10, then I can find AE. It'd be the whole thing 10 minus BE, which is X. So therefore, AE is 10 minus X. And if AE is 10 minus X, AF will be the same thing. Because again, tangent lines that share a same endpoint are congruent. Next, I'll find DF. Well, for DA, we have a full length of 18. For AF, we have 10 minus X. So if I take 10 minus X away from 18, I'll have DF. So therefore, DF is 18 minus 10 minus X. And that's true for DG as well, because both are tangent lines and both share a common endpoint. I'd like to continue going around this direction, but I don't have the length of CD. So therefore, I can't go any further this way. So at this point, I stop, I go back to where I started, and I go around in the opposite direction. Now, depending on where you start, you may be able to go all the way around without stopping. This isn't one of those cases, though. So I go back to B, and this time I'm going to go around clockwise. So I know that BH is X, and BC is 15. If I want to find out what CH is, I'll do the whole thing of 15 minus BH, which is X, giving me 15 minus X. And that's true for CG as well, because tangent lines that share a common endpoint are congruent. Lastly, I have two parts of CD, so I can go ahead and solve for CD. CD is equal to 15 minus X plus 18 minus 10 minus X. From here, it's extremely important that you distribute the negative through the parentheses. So I'm just distributing the negative through. That will leave me with 15 minus X plus 18 minus 10 plus X. I have a negative X and a positive X, so they cancel each other out. And that's why it's so important to distribute the negative, because if you don't, that won't turn to a positive X. From here, I combine like terms. 15 plus 18 is 33. 33 minus 10 is 23. So our final answer for this segment, CD, is 23 units total. Let's go ahead and try out another. Same type of thing. We have ABCD is a quadrilateral, and it is tangent to the circle. AB is 20, BC is 11, DC is 14. We would like to find out what AD is equal to. Go ahead and take a minute, try it on your own, then we'll go through it together. Now, as you guys are working on this, you may get different answers than me as you draw it up, but the main thing is that your final answer is the same. Because depending on where you start around your circle, you may get a different setup than me. But as long as your final answer is the same, it'll be the same type of process. So starting with this, we want to find out what AD is, but we're given sides AB is 20, BC is 11, and DC is 14. Now, when I click my next button, all the work's going to show up, and then I'm just going to take it step by step. So keep that in mind. We're trying to find out what AD is equal to. So first thing I'm going to do is I'm going to call AE X. So let me go ahead and draw my congruency marks on here based upon our tangent C points. They share a common endpoint, and they're all tangent lines, so they're all congruent to each other. Well, each corresponding part is. So AE is congruent to AF. BF is congruent to BG, so on and so forth. Now, again, I'm going to call AE X. If AE is X, and then just bear with me now, if AE is X, then AF is X. Well, if AB is 20 and AF is X, I can find BF by doing 20 minus X. Now give me BF as 20 minus X, which would also be the length of BG. Now, if BG is 20 minus X, and CB, the whole thing, is 11, then I can find CG by doing the whole thing 11 minus BG, which is 20 minus X. So therefore, both CG and CH are 11 minus 20 minus X. Lastly, DC is 14 in length. HC is 11 minus 20 minus X. Therefore, if I subtract that HC from DC, I'll have DH. So I'll do the full thing, 14 minus 11 minus 20 minus X. That will give me both DH and DE. Now I can find segment AD. AD will be equal to X plus 14 minus 11 minus 20 minus X. All the work's going to go up, but then bear with me as we work through it. So again, AD is equal to X plus 14 minus 11 minus 20 minus X. Parentheses are extremely important here. The first thing I need to do is I'm going to work from my most inside parentheses outward. So I start by distributing the negative through, because there's nothing I can do within here. They're not like terms, so I just distribute my negative through. That will give me 11 minus 20 plus X. Combining like terms within the parentheses, 11 minus 20 is negative 9. From there, I'll distribute the negative through the parentheses once again, because now I have the second negative right next to it. That will give me positive 9 in negative X. So now I have X plus 14 plus 9 minus X. Positive X and negative X cancel each other out. 14 plus 9 will give us 23 units. So we got the same answer as our last problem, but again, we went through a different process. We started with different numbers, so we got the same thing down. So again, it's just random coincidence that we got 23 for both, but again, we just walk around these problems. Let's go ahead and try out our final problem for the day. We're going to find the radii of the three circles. We're given that AB is 8, BC is 13, and AC is 11. Now, since I'm trying to find the radii of the circles, I'm just going to start on one of my circles and call the radius X. So for circle A, the radius is X. Now, if this radius is X, again, the radius just goes to the edge of the circle. Each of these circles is externally tangent, meaning that they all touch each other at a single point. So therefore, if I want to find the radius of B, well, that would be 8, the full length of AB, minus the radius of circle A. So that'd be 8 minus X. And since it's a radius, it's going to be the same for both sections, up to the edge of the circle. So this portion is 8 minus X here. Now, if BC is 13, I can go ahead and find the radius of circle C by doing 13, the whole thing of BC, minus the radius of circle B, 8 minus x. That'll give me circle C's radius is 13 minus 8 minus x. At this point, I can go ahead and find the radius of each of these circles. So I know that AC is equal to 11. I also know that AC is equal to x plus 13 minus parentheses 8 minus x. So therefore I can say 13 minus 8 minus x plus x equals 11, the full length. First thing I do is distribute the negative through the parentheses, giving me 13 minus 8 plus x equals 11. Combining like terms will give me 5 plus 2x equals 11. Subtracting 5 from both sides will give me 2x equals 6, and dividing both sides by 2 will give me x equals positive 3, which is nice for us, but we're looking for the radii of the circle. So to find the radii, we just plug our values in. So for circle A, the radius is x, so therefore I know the radius of circle A is 3. For circle B, the radius is 8 minus x. Plugging in x, we get 8 minus 3, which is 5. So circle B radius is 5, circle A's radius is 3. Lastly, plugging in for circle C, we have 8 minus 3, which is 5. 13 minus 5 is 8. So therefore, we have radii of 5, 8, and 3. Again, circle A is 3, circle B is 5, and circle C is 8. All right, guys, thank you so much for watching today. If you have any questions, please let